So welcome everyone, and thank you for joining. So I'm excited to talk to you about graph neural network and large language models. So this is a collaborative work with Xiaoxin He, Brian Hoy, Thomas Laurent, Yann LeCun, and other collaborators. Okay, so here is the outline of the talk. So I will first introduce large language models. And then I will ask the question if we still need graph neural networks in the era of LLMs. I will review the advantages and limitations of large language models and graph neural networks to identify tasks where this combination can be useful. And in particularly, I will present two works. The first one will be to use LLMs for improving GNN reasoning. And the second one will use GNN for LLM reasoning. And I will conclude. All right, so I think we live in a very exciting times with the deep learning revolution compared to when I was doing my PhD. Computer vision completely changed with the introduction of deep learning, as you know. So it was in 2012 with ImageNet. Architecture at that time was convolutional neural network. Is still very powerful architecture. With AlexNet, 8 layers, 60 million parameters, 2 GPUs. And the industry quickly understood actually that that was going to be very productive to make money. So it works very well for automatic recommendation. It will work pretty well in autonomous vehicle, it's coming. And of course, for surveillance, this is a very powerful tool. The revolution for natural language processing came a bit later in 2022. So data set was internet, basically. The architecture was a transformer. And there was much more layers, like 100 layers and 175 billion parameters compared to AlexNet. Number of GPUs was also much larger, from 2 to 10,000. But it really created a new industry that we call generative AI for everyday tasks. For example, coding, text summarization, content creation, dialogue system, everything is automatic now with this system. And actually, people gave a name to this large pre-trained network trained on massive data set. This is called a foundation model. So we have now this generative AI industry booming. So for example, for text generation, we have proprietary LLMs with GPT, Gemini from Google, Claude, Anthropic, and Grok, Twitter. We have also open source LLMs. Thankfully, thanks to Meta and Yann LeCun, basically we are able to manipulate these LLMs, and this is fantastic for researchers like us. So Llama 3, Mistral, Gima by Google. Datasets are quite huge. But something also interesting is that the architecture has not very changed from 2020. So it's still a decoder. There are a few improvements, but basically this is still a transformer. The hardware has changed quite a lot. So it's 20,000 GPUs. If you want to buy it for yourself, so it would cost today like $4 billion US. And the next generation is going to be even larger with 100,000 H100 GPUs. For image generation, so we have also proprietary models like Midjourney, Flux Stable Diffusion, and DALL-E. We are not lucky for researchers because we don't have access to these open source models. Datasets are quite huge, and architecture also strangely is still transformer with some variants, but this is called a visual transformer, and we use diffusion models. So this is the new stable way to do to generate new data. Yeah. So these LLMs, they have been trained on internet basically, and we know that internet is a network, right? Is a network connecting web pages, and each web page is basically a text document with a lot of information. So, and then if you look at, for example, also Wikipedia, so you're going to have links inside the web page connecting to other Wikipedia pages. The same also if you take a JSON file. So there is a lot of JSON file on internet for the structure of websites. And when you open a JSON file, you will see links. So there is a lot of links. So basically what it means that LLMs have been trained on graph data, and a lot of graph data, because internet is not only the text, but also the connections between the text. So they have learned, the relationship between text data. So the thing that they have been trained on so huge, massive data sets, so they are able to, identify, for example, relationships between entities if you ask them, and also predict non-labels in a network, for example, of scientific articles. So when LLM came, basically with Xiaoxing Yi and my collaborators, basically we asked the question: do we still need GNN actually for reasoning over graph structure data? Because LLMs have seen everything, right? So they have been trained on internet, so they know graph data. So I was very worried, to tell you the truth. So in this talk, I'm going to focus on text attributed graph. So they are basically what we call textual graph. So each node is going to be connected to other nodes. For example, here, this is a knowledge graph. And each node, the feature will be text. Okay, and also the edge information, so the connection between two nodes, and the edge feature will also be text. Okay, so it's basically a topological graph, and on the top of it, you have a lot of text information. So we will not consider a non-textual graph like a molecular graph. This is not the goal of this presentation. Okay, so first of all, what we did was, okay, let's look at a popular data set and let's try to predict using LLMs. So the popular data set we used was the one from OGB. So this is OGBN archive. So this is a data set which is a network of scientific papers. So the number of nodes is 170,000, number of pages is 1 million. And here the task is basically a prediction task for the class of the paper. So we have 40 classes to predict. And the node feature are basically for each node, this is an article, so you have the title and you have the abstract, and you just want to predict, the class. So the results are as follows. So if you use a GNN trained on the bag of word features given by OGB library, basically you will get 70% accuracy. Okay. Now, if you look at the OGB leaderboard, the SOTA paper is actually a GLEM, which is a combination of a language model and a graph neural network. And the precision was 76.6% accuracy. Okay. And then what we simply did is basically we took at that time, it was 2022, we took at that time the best LLM, that was GPT 3.5. And we asked that, given the title, the abstract, and the 40 classes, to predict actually the correct classes. And he was able to do 73.5% accuracy. So the good news is that it's not better than the state of the art using GNN. It's still close, but I think this is that was a big relief, I think, for me, that we still need a GNN in the area of LLMs. Also, something that was interesting is that, of course, probably the OGB dataset was part of the training dataset of GPT 3.5. So remember, GPT 3.5 was trained on internet, and probably this dataset was part of the training data. So we have seen the test set, and this is what I mean. Okay, so now let's try to see how can we combine graph neural networks and large language models. So for this, we need to identify what are the strengths and also the limitations of these techniques. So large language models, they are really impressive. They are able to accurately model language distributions. So predicting the next word, given the context, they do that. It's very impressive. And they have been trained actually on everything, from human knowledge, which is on internet. So the way I see it for me is like, so you have the human knowledge, which is here, And then you have this LLM, which is some kind of AI oracle. Okay, so an oracle knows everything, you have seen everything. And then humans, we go to the oracle and we prompt the oracle, okay, give me an answer to my question. So it will answer something. Okay, so you can ask anything to an oracle, it will answer something. But the problem with an oracle is that because it has so much knowledge, you need to have a very precise, questions to the oracle. Otherwise, it will not give you the answer that you like. Okay. So, but still, that was very impressive at that time. So in 2020, when GPT 3.5 was released, so very strong zero-shot capabilities. So the scaling laws, despite some people can say today, for training and inference have not yet saturated. So bigger networks, larger data set, longer training time, longer search inference actually still improves the result. And it's very easy to see why. It's because companies, they are buying more and more GPUs. So we know that the scaling laws is not dead. The limitations, so we know that because, again, we don't know how to prompt correctly an LLM, they will make, errors. We call that gently hallucinations, but this is basically very bad answers. So they have logic. They have also limited logical reasoning. So, for example, there is Terry Tao, which is who is like a very strong mathematician. And he tried, the last version of GPT, and he said basically, they are actually very limited. Again, you need to give them a lot of precise prompt to make it work. So they have a limited logical reasoning. So what OpenAI tried recently to do is to improve that by learning, chain of thoughts, for example, and also for inference to do search algorithms. So it improves this limitation, but it's still not there. They have also limited graph reasoning capabilities, even, again, if they have seen the test set of the graph task during training. For GNNs, I think the strength is basically to be able, so if you have a graph like this and you have a question, for example, is the Mona Lisa in the same city as Alice's friend Bob? So you have here Mona Lisa, you have the city, you have Alice, you have Bob. So if you do multiple layers of GNN, what you will do, you will basically learn a multi-hop path that will go through the solution of your task. So they are very good to do that, and they are very effective for many different modalities. And now we're talking about text, but they are also very good for example, physics, biology, combinatorial optimization, and also chemistry. And we know that chemistry, that was the very good year for AI. So there was a Nobel Prize in chemistry for AlphaFold. And AlphaFold, as you know, is an edge transformer. So predicting the pairwise distances between residues in amino acid sequences. So this is a graph neural network, basically. Limitations for GNNs is basically they like graph foundation model in the scale of natural language processing and computer vision. Of course, the community has worked a lot on that. It's very interesting to push in this direction. But there is this emergent property, basically means that we need to go beyond the scale of training data and compute to get something very powerful. So we are not yet there. The problem is basically, the data set. We don't have like large data set available. OGB, is still comparatively small compared to ImageNet, which has 150 gigabytes of images. The hardware for running sparse linear algebra is not optimized. It's much slower than standard dense operations. Existing pre-trained GNNs, because basically of that, they are small. They are not doing billions of parameters. This is basically millions of parameters. And I think also something which is today, which is a limitation, is that industry has not yet found some interesting application of GNN, because industry is really driven, the AI research and AI product. Why we have GPT today is because industry got interested in deep learning, and then also to develop, product. So it's not yet clear, how to make profitable stuff from GNNs. It will come, I think, but it's not yet there. So combining LLM and GNNs, basically, it means developing training a joint text and graph foundation model. And this is, of course, a very attractive idea, very promising idea. But today, I think the issue is that there is a very huge imbalance between the knowledge coming from text, from LLMs, and the knowledge coming from GNN. So of course, what we would like to do is to do this kind, of architecture where we have the text, then the text will go through an LLM, it will process it, it will give us some vectors. The same also for graph, it will go to the GNN, will process it, will give us some vector, and then the vectors will be processed together with self-attention or cross-attention, and we need, for example, if we do text generation. So the fact that we have a huge difference between these two domains, I think this is very challenging. So what it means basically that we need to tailor, the combination of LLMs and GNNs to get some value of that. So for example, what we can do, we can use the LLM using the vast knowledge of LLM and then try to improve the performance of small scale text attributed graphs. And we can also do the reverse one that, we can use a knowledge graph, for example, to constrain the LLM to give more precise response. Okay, so reducing hallucinations this way. So this is what we will do next. So we will review two works that we have done, and this is really focusing on text reasoning task. So the first work will be we will use LLMs to enhance GNN reasoning. So this is a work basically that is taking LLM reasoning abilities to improve GNN predictions, and it's pretty actually effective and robust. The second paper we will review is basically a GNN will enhance LLM reasoning. So this is a foundation work where we try to put together all the benefits of LLMs, GNNs, and also something that we call GraphRAG that I will explain. Okay, so let's see the first technique here. So the technique is called tape. So here the idea would be to use LLM knowledge to improve the quality of the node features in a tag. Okay, so if we have better node feature, then we will be able to predict, with more accuracy, with higher accuracy. So the question is, how do we extract again information from an LLM for a specific tag task? So to do that, we are going to prompt the LLM, because LLM are again accumulated so much knowledge that what we would like to do is to prompt the prediction of the LLM, but at the same time, we also want to understand its reasoning. Okay, so we will ask so given, for example, an article, the article would be the title, the abstract, we will ask the prompt question, so basically predict the class, but at the same time, we will ask the LLM to give us, its reasoning. So why did you decide for these predictions? Okay, so we call also reasoning or explanation if you want. Okay. So now that we have the sequence of words for abstract, title, explanation, prediction, this is not something that we can directly use with GNNs. So what we need to do basically is to have a mapping from sequence to vector. Okay, so we want to take this input sequence of words and then output a d-dimensional vector that will summarize this information and that will improve basically the expressivity of this node feature. So remember that in this example, a node is an article. Okay, this is another article, and then what we want is to predict if there is a relationship. No, I'm sorry. And what we want to predict is, the class. Okay. So what we propose something that is going to leverage both proprietary and open source LLMs. So this technique is a kind of interpreter between a closed LLM and an open LLM. Okay, so the closed LLM can be GPT, that can be Gemini. So we know that these proprietary LLMs actually are better than the open ones. Okay, so we can go on the leaderboard of LLMs, and you see that always the top two are GPT and Gemini. Okay, so unfortunately for researcher, proprietary LLMs, they are better than the open ones. But the problem with the closed LLMs is basically that they only provide sequence of words, right? They don't provide the vectors that we want to train the GNN. So in contrast, if you look at the open source LLMs like Llama or Gima, basically they are going to provide the text, but also the vectors, right? So we have access to everything inside the architecture. We have the hidden vectors, the hidden features, but also the the output. Everything is given to us. So what we decided to do in 2022, so at that time, GPT 3.5 was the best closed LLM. So this is the one that we used. So we have our article. So this is the node I in the graph. Given the title, the abstract, we query, we get the explanation, we get the prediction. And then what we do is that we are going to convert the sequence of, for example, of words in the prediction by using a language model, so like a small one, which is DeBerta in this situation. It has 129 million parameters. And here, let me zoom in. So what we do is basically, so we have our sequence of word tokens. So this is basically the explanation if you want. And here we have, in any transformer architecture, you can have a class token, basically something that will summarize the sequence of words. So we give as an input this, we go through L transformer layers, we output, and then we get the class token after L number of transformer. Then we go through an MLP, a small MLP, to fine tune on the training set. Okay, so the training set, we know the correct class. So we want basically to fine tune the MLP on the correct class of the training set. So in the MLP here, it's a small one, only 2 layers. The first layer basically will just be some features, and then it will go through another layers to get the number of classes. So for example, that can be 40, 7 if it is Cora, 40 if it is OGB archive. So this guy here is going to be a vector of 700 dimensions. So this is actually going to be our enriched feature. So this feature will represent the input sequence that we have here. Okay, and this is very tailored to the task that you want to solve. Okay, so this way we are able to get enriched feature for the explanations, enriched feature for title abstract, and then we can also have prediction feature. Okay, so what we should do if we are in 2024, actually we should change the small DeBerta language model by now using a large language model. Okay, so why we can do that at the university is basically if you take, for example, Llama 2 or Gima, you can fine tune them using this very nice technique of LoRa. Okay, so low rank fine tuning, and basically with my small GPUs, actually I'm able to fine tune a large language model like Llama 2. So this is very great. Okay, so basically what we will do, we just need to change the proprietary LLM with the best one. So you take the one that you like, and then here instead of using the DeBerta, you can use Llama 2, for example. Okay. So once you have your enriched node features, what you're going to do, you are going to train your GNN, okay, with these new node features. So you can use your favorite GNN, okay, and then you can make the prediction. So we can compare the quality of node feature now. So we are going to see shallow feature, language model, and large language model features. Okay, so the shallow features, so if you look at OGB dataset, so they have already designed some nice handcrafted features for each dataset. For example, this is skipgram for OGB archive. And what happened is that you get 70% accuracy on the test set in only 4 minutes. Okay, so this is very fast, and I think this is a very good baseline for model performance. Now, as I said before, the state of the art is GLEM, and GLEM was training simultaneously a language model, okay, and also a GNN. And basically this model got the best, accuracy of 76.5%. But of course, because you need to train, your language model, this is going to take more time. So it's going to take, 9.2 hours. Okay. So there is here at that time, before the introduction of ChatGPT, there was really a huge trade-off between, if you want to increase your accuracy, you need to pay the price of, much more computational, hardware, but also training time. So now this is what we suggested. Basically, we use this LLM, we prompt them, we translate into vectors, and then we fine-tune. So accuracy was 75%, and only 3 hours to do that. So interestingly, once we published the paper, so we got at the top one of the leaderboard, and then there was other techniques that used the same approach, of course, a little better. And then now the top 3, even today, actually, I was surprised. I look at that recently. So even today, the top 3 models for OGB archive are basically based on this technique. Okay. So of course, one reviewer number 2 say that, oh, we cannot trust your results because OGB archive is part of the LLM training data set. So we cannot trust you. So what we did basically is that we produce a new OGB archive, not OGB archive, but an archive data set. We called it Tape Archive 23. So it's available to download. We have 77,000 papers, same number of classes. And basically, we have the same conclusion. There is nothing that changes when we do that. And again, this is also the reason that an LLM is, even if it has seen, the test set, is not able to reason very strongly with graph structure. So you still need the GNN to use the topological relationship to make good prediction. We did some ablation study. What we observed is that there is no specific feature which is better than the others. It's actually the combination which is important. So intermediate conclusion for this work. So basically, we can use the LLM knowledge and its reasoning abilities to enhance the node features of the tag, and also the make it to fine-tune to the specific task. Okay. So what we did is something like is not end-to-end. So we don't train everything together. It's actually, we first generate good features, and then we train the GNN. So this is, I think, along the trend now of LLMs. So basically, LLMs is not trained end-to-end. They are like 4 steps: self-supervised, fine-tuning, reward model, and finally reinforcement learning. Okay, so each step is done independently, because each step is very clear to do it, to train. And I think, it's very stable. And this is exactly the same conclusion that we have here. We can make it very stable and it's efficient. Everything which is stable will have better performance usually. Okay. And also something interesting is that we can leverage both actually proprietary and open source LLMs. So we have the best of the 2 worlds. It's also, of course, some people will like it. It's interpretable because you can see the reasoning, words of the LLM. Okay, so now let me go to the second technique that I want to introduce. This is called G retriever. And the idea is, as I told you before, is that LLM is very powerful. It knows everything. But the problem is going to make errors because we never have a good prompt in some sense. So we need to constrain, to regularize, the LLM response into a much smaller space. And to do that, actually, we are going to use, a tag, text attributed graph, like a knowledge graph, and it will force the LLM basically to answer related to this tag. Okay, so the key question is, of course, how do we extract pertinent information from, a graph, and to force the LLM to be more focused? Okay, so to do that, we are going to use the tokens. So I think now everybody understand that, so because of the transformer architecture, what is very nice is to work everything as an input, right? So the input of your LLM can be, of course, your query token, but it can also be other information like visual tokens and also graph tokens. So this is what we're going to do here. We are going to use two kinds of tokens. So the first one will be, and I will explain that in the following slides, a graph encoder token, which is going to be here, and then a text-based token, which is going to be here. Okay. So the graph encoder token is something very natural. For example, if you do molecular science, you want to represent your graph as one vector, and then you use this one vector to make a prediction for the property that you want. So here this is the same idea. So we can select any favorite GNN. We apply multiple graph learning layers to compute a very deep node hidden feature. You compute then the mean over the nodes, and then you apply an MLP, a small MLP on that. So this way you will have a graph encoder token that summarize your topological graph and also the feature on your graph, and with one vector. Okay, so this is going to be this guy of d dimensions. The other thing, of course, is that an LLM wants to use word tokens, right? So the information, the way it processes information is by using words. So we need to, if you want to have access to tap, to the knowledge of LLMs, we basically need to transform the graph and its feature into a sequence of natural language tokens. This is important to do that. And so, for example, here you have a graph, and you can represent this graph by some textual representation. For example, a graph G is a set of directed edges defined by ij, where node I points to node j. So here the graph G is defined with edges 0, 4, 1, 6, and so on. Okay, so you have a one-to-one mapping between this mathematical representation of the graph and this text representation of the graph. However, there are many ways to use language to represent graph. So for example, in this paper, they have this nice example to show, oh, you have many representations. So the text-based representation of a graph is not unique. Okay, so this can be an issue. The other one is also what I say is not text equivariant. Okay, it's not text equivariant in the sense that if you change, this guy by this guy, you will have probably different results. Okay, so we want to have some kind of equivariance for the text representation, but we don't have it. The other thing is a scalability issue when you want to represent a graph with text. Okay, so if you take an open source LLMs, the context window is limited, right? So for example, if you use the one that we use in academia, Llama 2, so basically this is 4,000 tokens of limitation. So if your graph is small, no problem. But if your graph is, for example, the Wikipedia graph, then this is like a huge number, of nodes and huge number of edges. So this is not something that you can do. There is a scalability issue. Of course, LLMs are prone to hallucination. So for example, here we have an example that an LLM can produce nodes and edges that do not exist actually in the knowledge graph that we use. So if in the vocabulary of the graph, we have some, for example, here the one deer doesn't exist, and is still, it's part of the vocabulary. So the LLM can give you actually this entity here, which doesn't exist. So what we propose is basically, so first we are going to apply a GraphRAG that I'm going to explain how we do that, to retrieve a subgraph from possibly a large text attributed graph, which is going to be relevant to the query of the user. Okay. Step 2, we are going to concatenate the user query, but also the graph encoding token and the text-based graph tokens to create the input sequence of the LLM. Okay, then step 3, the LLM will give us, will generate an answer. Step 4, we will train everything. So we will simultaneously train the GNN parameters, and also we'll fine-tune the LLM parameters using LoRa. And the good thing is that you see, if you use LoRa, you're only using 0.5% of 7 billion parameters. So it's only 35 million. And the GNN has something like 5 million. So it's not that much actually to train. So this is something we can do in academia. So the GraphRAG that we propose, so this is a graph retrieval augmented generation. So RAG is today very popular. Here we want to extend to graph. The main problem is, of course, the scalability. So I'm going to tell you how we solve this problem. So yeah, let me maybe go here. So the first thing is to do indexing. So what we do is that we're going to have a text attributed graph. So we're going to take the node feature. So this is the text node feature. We have also the edge feature, the same. So we will apply a pre-trained and frozen large language model or small language model. So at that time, we just use a small language model. But we can use a large language model now. So you do that, and you get some d-dimensional representation of all the nodes and of the edge. Okay, and you store them in a database, in a graph database. So today we are lucky. There are many open graph databases that can be used. So for example, PyG, DGL, but also Llama, Index. Also there is Microsoft and Nebula Graph. There are also some proprietary graph database like Neo4j. Okay, so we do that. So we take this and we have vector representation of the node and the edges. Okay. The second thing is that we are going to do retrieval. So given a query from the user, we will represent to the query, for example, what is the name of Justin Bieber brother. So we will use the same, language model to represent the query as we did for the node and the edges. Okay. And then what we will do is basically we just do a similarity metric evaluation. So here we just use a cosine metric, and we can retrieve this way the top k nodes and edges from the graph database. Okay, so we will get something like this, which is a noisy, I would say, subgraph. And then the next step would basically to extract just a smaller graph which has the most relevant information, and that's it. Okay, so the way we do that, we are going to solve the price collecting Steiner tree. Okay, so the price collecting Steiner tree is basically a tree. So if you start from this original graph, and then each node has a price. So the higher the price, the more important you want to be in the tree, in the final tree. So you can solve, you want to maximize the price, but also you don't want to take everything. So you are going to have a penalty with the cost of the solution that you want. So usually this is, you don't want to, or it should be minus, I'm sorry, it should be minus here. So you don't want to take too much nodes. So basically this is the number of nodes that you have here. Okay, so when you solve this combinatorial optimization problem, which is NP-hard, but you can have an approximate solution using semi-definite programming SDP, you will get something like that. Okay, so this is a directed tree, and you see that the directed tree usually has some kind of root node, and it flow out, for example, and of course he wants to take the larger nodes. Okay, so this is the original Steiner tree. We can modify it because here there was only the nodes. But of course, when we do graph learning, there is also the edge feature that we want to use. So we can incorporate, you can easily incorporate edge information. Okay, so we have a price also for the edge. So you see, this is, for example, an edge which is more important than this edge here. And we just, modify a little bit the combinatorial optimization problem here. And we can solve it, using a very fast technique. So this is very the approximation is near is the most linear time approximation. Okay, so if we compare the standard RAG with the GraphRAG, so the standard RAG basically you will have your knowledge database, and then you will extract the number of relevant documents that you want. For the GraphRAG here, so we have also a graph database. And we are going to extract a much smaller but very relevant graph related to the query of the user. Okay. So now I'm coming back to the tokens of the input LLM. So the first one, again, this is the graph encoder tokens. I already talked about this. So this is, an MLP on the mean of the the node the node hidden feature at the last layer of the GNN, and it's going to be here. So this is something, of course, if you have learnable parameter here, everything can be changed, you know, by backpropagation. So for the text base, basically we will have two sequence of input words. So the first one is the query of the user, what is the name of Justin Bieber brother. And the second one will be the textualization of the graph. Okay, so this is something again that is important for to use the to tap the LLM ability. Okay, so we do that. So we have the graph representation. It will go through the text embedder. So any LLM has this first layer that is doing to do the word embedding. Okay, so here token embedding, and then it will go through, you know, the LLM. So the training is very standard. So we give these input tokens. We have the transformer layers, and then the system we generate recursively the response. Because we know the label using a training set, we can basically fine-tune the system to give us the right answer. Okay, so we can again, we are going to compute the cross-entropy loss with respect to the generated answer and the ground truth, and then we are going to do the backward pass to compute the gradient and then update the parameters of the system. So for GNN, but also for the LLM. Okay. So in summary, GRetrieval is composed of 4 steps. So we have GraphRAG, which are this here, which is for subgraph retrieval related to the query of the users. Then we have computation of graph tokens using a GNN. We have also response generations once we go through you know, the input tokens and also the transformer layers, and finally model training. Okay, so here we try to combine you know, the best of all worlds together, and I think this is done in a very natural way. Yeah, we have to change the existing data set and create a new benchmark to evaluate this you know, this task. So doing the reasoning of text attributed graphs. Yeah, so we have different things: explanation graphs, scene graphs, and web QSP. So the main results are basically that, okay, here there are many things, but you should only focus on that. So if you do our technique GRetrieval, basically you will be able to beat if you only do LLMs. So you have your LLM, you query, and then you get the answer. If you do only the GNN prompt tuning, so we still do better. And if you only do the LoRa fine-tuning LLM, so we still do better. Okay, so this is really trying to combine the best of these worlds. Okay, so the scalability is basically now we are able to, for example, only use, you know, reduce by 83% and 99% the number of, you know, the number of tokens, the number of nodes that we use. So instead of taking, you know, the whole Wikipedia graph, we will only take, you know, a very small subgraph of the Wikipedia network. Yeah, of course, the one that we were interested in is, does it improve hallucination? So we compare with the baseline, which is just you doing LLM with query, and we manually. So what we did is that we asked, you know, 100, we did 100 queries and then 100 responses, and we look at manually if you know, there is some missing nodes or adding you know, wrong nodes, and the same also for the edges. And we see that if you use GRetrieval, you really reduce the hallucination. Ablation studies. So what we observe basically is that, and that was very interesting, is so the token given by the GNN and the tokens, the text tokens of the graph, they are actually contribute equally. Okay, so the information coming from the GNN and the information coming from the text and the LLM of the graph is they are basically both important. Okay, so they are complementary, they really improve everything. So I think it makes sense, of course, because you have your GNN, we know that they are pretty good for extracting graph information, but also the LLM has a very strong capability with, you know, with text representation. So the two are complementary. So in conclusion, if we want to unlock the LLM capability, we need to use, graph as, represented as token, as words, but actually combining everything. So the LLM, the GNN, and the GraphRAG provide superior performance. So it's not only the LLM capability that does the work, it's actually many others. So GraphRAG is effective, efficient, and mitigate LLM hallucinations. So here are the paper, the code, and I really invite you to read the blog post by Xiaoxing He. So she has done a terrific work here. She's the main researcher in this project, and she received for this actually the 2024 Google scholarship. So I really invite you to read a blog post if you want to have a high-level introduction of this. So also, the PyTorch geometric team, they included the G retriever, so this is very nice. And I think also something which is very interesting is to look at, again, we always go back to the question, can we use GNN to improve products, right? And I think here there is an opportunity. So if we look at the history of web search engines, so everything starting with, Google PageRank, they didn't use any text processing. Then there was Word2Vec. They use Word2Vec. Then they use language model. They use also RAG. And finally, we have Gemini. Okay, so Gemini is LLM plus RAG. So LLM, if they don't know the answer, they will look at RAG when you prompt Gemini. So the next step, hopefully, would be to use GNN and some text attributed graph, knowledge graph that would be useful for web search engine. So here, what is attractive, I think, is that everything is integrated and learnable. So this is deep learning. So the next step, of course, that we are working with Xiaoxing is basically okay. So we have the text the text feature, we have the graph feature. So the last feature you want is basically doing the image, introducing the image information. So again, today everything is a transformer. So what you can do is that you can take your image, you can decompose your image into patches, and then your patch can be represented by just a vector. So this is a visual token, and then you go through transformer layers, and you backpropagate also to update the representation of your the parameters of your visual transformer. And that's it. So thank you so much for being there, and I'm happy to take any questions.